this area under curve represents, this is like absorbance value. In case of absorbance value, we get always less than 0.1, so less than 1, so that we can apply Beer-Lambert's law. It usually is agreed like that. So here also the chemical shift value, whatever we are getting, area under curve at a particular chemical shift value, if it is representing one proton, let us say here a proton like this, a aromatic proton, then area under curve represents how many moles of compound is there. Okay. So here one more thing is, all the values that we are getting in NMR, including the delta value, like a chemical shift value, they are all relativistic representation. They are not absolute values. They are relativistic representations. Okay. So that is the reason why we require an internal standard. Internal standard is almost essential in quantitative estimation of any compound by using qNMR technique. That means, let us say we don't know the concentration of a particular compound. Okay, absolutely fine. But to the compound mixture, let us say if you add an internal standard of known quantity, add a internal standard of known quantity, then area under curve for a particular compound that is used as internal standard, that is taken as standard, and then with respect to that, how many moles of test sample is there? That is the way how evaluation is done. Because in case of internal standard kind of quantitative analysis, this is the way how we go ahead. So let us see, with a case study, you feel like it is reasonably easy. So here, in case of NMR, what is the advantage that we have? The possibility of determining structures at a molecular level. Let us say if you an NMR is given to you, it directly tells you whether a compound is there or a mixture of compounds are there, or how many compounds are there probably, also can be obtained. And then here advantage is there is no need to intensity calibrations in case of determination of ratios, because it is a relativistic representation with respect to tetramethylsilane. That is what we use in case of proton NMR. Okay. So the proton values, whatever are there, they can be directly taken into consideration, provided their signal to noise ratio is good. Relatively short measuring times, because here we are using proton NMR for the analysis. For the entire scanning, let us say 16 scans, let us say if you take, the entire analysis can be concluded within 5 minutes. It is a non-destructive technique. So if a sample is more valuable, then you can recover the sample, absolutely fine. No prior isolation of the analyte is needed. Okay, so if an extract is given, if a serum sample is given to you, or a urine sample is given to you, or a juice sample is given to you, imagine the complexity of the chemistry involved in those samples. They can be directly taken into the NMR tube, add necessary deuterated solvent, and go ahead with your analysis. There is no need for isolation of the sample is needed. The possibility of simultaneous determination. Let us say, for example, if you are given with a formulation where more than 2 chemicals are there, 4 chemicals are there, absolutely fine. For all the 4 chemicals, if you are able to see representative signals in the NMR, directly you can go for simultaneous estimation of those chemicals in a complex mixture. For example, urine analysis is done by using qNMR, NMR only, but quantitation also can be added. More than a dozen chemicals were simultaneously estimated. Okay, so those reports are also there. So with the entry of NMR, as we all agree, the pace at which chemistry research is happening, chemistry related research works are happening, has increased significantly. So qNMR is not a latest technique, but it is one of the oldest techniques that we have, because it is after all an absorbance based spectroscopy technique. So research is going on. So from 1950s onwards, if you closely observe, the number of samples that are analyzed for both qualitative and quantitative analysis increased. So qNMR techniques now, they are a lot improved. So more and more number of samples are now processed through qNMR analysis. Okay. So usually how we do the qNMR analysis. The first sample is like, let us say if you take an example, like a tablet is taken, then you have to first fix the solvent. So in which solvent we can run the analysis. So once that is done, fix the internal standard. What type of internal standard can be used? And then you go for weighing the sample by using a balance with highest precision. Okay. So that we know how much sample that we are taking. Just like in case of Indian pharmacopoeia, let us say if you are performing assay of diphenhydramine, then what is written over there? Take 20 tablets, triturate it, and then take 500 milligrams equivalent diphenhydramine powder. Okay. So tablet powder is weighed, and then we go for analysis. Okay. They're weighing. For weighing, we use precision balance. Here also the same. And then once the weighing is done, prepare the sample, maybe in 1 ml or 2 ml as per the requirement, and then transfer sufficient quantity. Because when you are preparing a solution, you are already aware of the concentration of the sample. Okay. Let us say labeled claim is 500 milligrams. Let us say you presume 500 milligrams, and then you are preparing the solution of known concentration. Then you will be adding internal standard to that, okay, of known quantity. Then you go for proton NMR, okay. So once you have done the proton NMR, you go for data analysis, okay. So, and then you will get the result. It is as simple as that. So internal calibration standard is needed. It can be a certified reference material. So in US FDA and other regulatory agencies has proposed a list of internal standards that can be used in qNMR. Okay, it does not stop you from doing research work. We ourselves have also we are also working on using internal standards, different internal standards, which can help us in for the efficient analysis of samples. Because if you go into the market, different type of samples, heterogeneous samples are now analyzed. So for them, all internal standards are not suitable. So we are also doing research work on that. Internal standard can be used. The qualities that are needed for internal standards are the same as the qualities that are needed for primary standard that we see in our pharmaceutical analysis. Only one calibration standard is needed. Let us say even if your formulation has, let us say 10 ingredients, for simultaneous estimation of all the 10 ingredients, you require only one internal standard. Absolutely fine. So internal standard is a different analyte, okay, and we are going to calculate relativistic calculations like internal standard with reference to that how much is the concentration of your sample. So this is the reason why we need not go for calibration curve. An additional advantage is validation of qNMR integrals of multiple signals can be used, because a compound is represented not by a single signal. Let us say just now we have seen a sample, flavonoid sample giving you 10 signals. So we can use one signal or multiple signals to represent quantitative presence of a particular compound. That is again another advantage we have. We can use one signal, two signals, or multiple signals to correlate quantitative presence of a compound. These are some of the internal standards that we use normally. If the sample is highly nonpolar, we can use highly nonpolar internal standard, which goes freely into chloroform or CDCl3. Let us say if the sample is highly polar, then we can go for water soluble compounds like sodium acetate can be used, dimethyl sulfate, fumaric acid, or malic acid. All of them, which are all water soluble, can be used. So in case of qNMR, how do we actually do the analysis? What do we do? First, we take the NMR of the test sample. In NMR of the test sample, we have, let us say, just now we have seen for flavonoid 10 signals were there. For all the 10 signals, we verify the signal to noise ratio. Signal to noise ratio is calculated, means how pronounced how strong the signal is in the sample. For example, let us say if we have a methoxy signal, OCH3 signal is there, which is not having any capacity to undergo any physicochemical change. Okay, so that will have more signal to noise ratio. But COOH signal, if it is there, carboxylic acid, that hydrogen is constantly undergoing hydrogen bonding interactions. So it cannot show 100% presence in the NMR, proton NMR spectrum. It is a very complicated situation. So those protons cannot show very strong signal to noise ratio. Those signals are now, we avoid those signals. So signals like protons present on benzene ring, protons present in methoxy group, protons present in alkyl chains. So they are suitable for quantitative analysis of a particular compound. They represent 100% the sample concentration. In case of standard also, we follow the same protocol. Let us say if we are using a standard, standard also can have more than one signal. There also we pick up a signal which has strong signal to noise ratio and also which is not interacting or interfering with the sample NMR signals. So we need to see zero interaction is there between standard signals and test signals. So once this is done, we can go for simple quantitative analysis. So once the quantitative analysis is done by following ICH guidelines, we can do all the tests for validation of the method. Just like HPLC method, because HPLC is one of the most popular techniques that we have. So for validation of that analytical technique, whatever protocols are there, here also we follow the same protocols like specificity, linearity, LOD, LOQ, accuracy, etc. Okay, so this is the way. So this is an example where we took lamivudine. For your ease of understanding, I am giving one example. Let us say if you take lamivudine, lamivudine is an antiviral drug. Okay, so it has so many protons. So here you can see in the proton NMR, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 signals are there. So in all these 11 signals, whatever signal that has very strong signal to noise ratio is to be taken into consideration. So here we have the signal that is connected to nitrogen. This signal is what we have taken into consideration. Okay, because it has very good signal to noise ratio and it is away from the remaining signals. So this signal, we can take one signal or more signals. So this signal is because of one proton that is present at the 6th position. And for internal standard, we are using imidazole. Imidazole is an experimental internal standard. We are the first to use imidazole as internal standard. So here, because this is a symmetric compound, we get one signal for the proton present on 2nd carbon and one more signal for the protons present at 4 and 5 positions. Okay, so this is one of the signal. This is the second signal. Okay, at 7.647, one signal. So its area under curve is 1. So here 1.96 approximately close to 2. Okay, 2 protons. So this is for NH. So this is, for example, this cannot be taken, NH cannot be taken for to be considered as a signal to be used for quantitation because NH can be hydrogen bonded. Now, if you mix standard with the test sample, how does it look like? So here I am just showing you the signals that we have taken. For example, let us say if you take here at 7.8, we have a doublet, okay? And in the nearby region, we don't have any other signals, but one more signal is over here. Okay. After 7.5 and below 8, only one signal is there. So here you can see after 7.5 and below 8, now we have two signals. So this signal is the proton present at the second carbon of imidazole, and this is the proton present at the sixth position of lamivudine. So these two signals can be used for quantitation of quantitative evaluation of lamivudine. So this proton signal at 7.61 approximately is actually representing imidazole. Okay. Let us say if you had taken 1 mole of imidazole, and if the area under curve is kept at 1, okay, and if for this doublet area under curve, if it is coming as 1 again, means both these signals are having same area under curve. What does it indicate? Both signals, if they are same as far as area under curve is concerned, both shall be present in the sample in the same concentration, because area under curve directly is connected to molar presence of a particular proton. Okay, because we are having here one proton. This proton represents the entire molecule as far as this signal is concerned. Okay, it is as simple as that. Let us say if you take imidazole 1 mole, area under curve is 1, and we don't know concentration of this compound. If the area under curve is this compound is 0.5, for imidazole it is coming as 1, and its molar its concentration is 1 mole. Then if its area under curve at 7.8 is 0.5, then its presence will be, its concentration is 0.5 moles. It is as simple as that. It is straightforward. Okay. So that is the way how we do the calculation. Now we just take it further, because here, why did we fix this signal and this signal? Because they are not interfering with each other. Their area under curve, their signal to noise ratio is very good, and they are responding properly. Okay. So there is no deviation. Now we have to verify whether the choice that we made for quantitative evaluation is correct or not. Validation is to be done. First point is specificity. Specificity is done by repeating the experiment with the known internal standard, weight of lamivudine, and then area under curve is taken and then calculated. Percentage recovery is calculated, just like in case of HPLC. And then if it is within the limits of pharmacopoeia, then we can go ahead, or the guidelines, whatever respective guidelines that we are given. Linearity. If more concentration is taken within the limit of concentrations, is it agreeing with the Beer-Lambert's law or not? We have to verify. And then limit of quantitation, limit of detection. So here a small changes. Here signal to noise ratio is taken into consideration for qNMR method, both for LOD as well as LOQ. Here signal to noise ratio is need to be kept at 150 for LOQ, 120 for LOD. So here we found like for LOQ 1.85 milligram per ml is needed for LOQ, and LOD is 0.05 milligram per ml. So this is what we found. And this should tell you one more thing. For HPLC analysis, limit of detection or limit of quantitation are in the microgram level. Okay. The only problem with NMR is not a sensitive technique. This is not a sensitive technique. Mass, HPLC, etc. are highly sensitive. That is the only problem with NMR. But if your sample size is good, then NMR can help. Then we go for accuracy by following the same protocols as in case of HPLC. And then precision also is done. Then solution stability is a very important concern for us. So here we have to prepare the samples and then verify whether the sample is stable or not. Especially In case of water as DMSO as solvents, we found many compounds, they get degraded or they give multiple signals, especially sodium acetate. If you take and prepare solution in D2O, because sodium acetate is salt of strong base, weak acid. So it will be in kinetic equilibrium because it will dissociate and it will be in kinetic equilibrium with sodium hydroxide acetic acid. That is the problem with the sodium acetate. So we fix the time limit up to which the standard solution can be kept. Robustness. In case of robustness, because in case of NMR, what are all the variables that we have are to be taken into consideration? We are using number of strands. Default value is 16. So we change them 8 and 32 and we have to verify. Spectral width. In case of proton NMR, spectral width is always taken as 0 to 20. Usually it does not affect the quality of spectrum. Whatever width that you have taken, it usually don't affect the quality of output. Relaxation delay means between each signal, between each scan, how much time we have to spend. 20 seconds is optimal for qNMR because it will ensure complete relaxation of the protons, so that for there will be no interference between scan to scan. Then number of data points. So it is more like resolution. Okay, so data points also they usually don't affect the qNMR method. Offset value, then receiver gain, RG value, exponential function, and then solvent that we are using. So all these are the factors which are to be verified in verifying the robustness of the method. Okay, so you can find some similarity between HPLC or other methods with NMR, but this is what we are supposed to do in case of qNMR method. Then once the method is validated, we use that method for assay of tablet. So in case of tablet, every pharmacopoeia it offers, let us say if a qNMR method is there, they will offer the protocol, how many tablets to be taken, etc. Here we are developing the method. So we have taken 4 tablets. For them, we have done 4 analyses. The claim is verified. And then we found it is in the limit. Usually in the literature, whatever is generated in the last 20 years, qNMR method is found to have highest accuracy, highest precision, highest dependency as far as analytical methods are concerned. So that's the only issue with the qNMR is its sensitivity. Let us say if your sample is in, like, let us say serum sample of a drug you are supposed to verify. If the serum sample is in nanogram level, nanomole level, then only method that we can apply over there is LCMS. We cannot use NMR for such a analysis, analytical protocol, because sample is to be concentrated, okay, so that it will come up to at least 1 milligram per 1 milligram level, okay, because for proton NMR we usually take 5 milligram for analysis. We can go up to 0.5 milligrams, not below that one. Okay, so there is that is the limitation with the qNMR. And as I told you, NMR can also be used for qualitative analysis. Qualitative analysis means if a mixture is given to you, by just looking at proton NMR, you will be able to say something about the chemistry of the mixture. So here we actually have done an industrial sample that is the lemongrass oil, and in that we found in case of lemongrass, what we used to have? Citral, nerol, geraniol. Okay, citral A and citral B. So here, by using proton NMR, we are able to find both the mixtures, citral as well as geraniol, and also there is an error in the structure. Okay, please pardon me for that. Here we will have a proton. Actually, the H is missing. Here also H is there. So this is so here aldehyde protons are there. These aldehyde protons usually come at 10. So we have two signals are there. This indicates one is citral, another one is geranium. Okay. Here we used toluene as the internal standard. So it gives us freedom to choose internal standards, provided if the internal standard qualifies for all the characteristics that are given, especially by the standard these regulatory agencies. So friends, we are almost at the end of the presentation. In case of qNMR, sample preparation procedure is reasonably simple. We need not, because as I told you, we cannot analyze samples like serum samples, etc. for drug metabolites. Okay. So we require very high frequency instruments for that. Because that costs a lot, it would be suggestible to go for LCMS, etc. Except them. Let us have an industrial sample like bulk drug sample, formulation, complex herbal mixtures, etc. If they are there, sample preparation procedures are reasonably simple in qNMR. User-friendly instrumentation and operation. Please, I don't say like NMR is affordable. I'm not commenting on affordability because it costs about right now 2.5 to 3 crores. Okay, that is fine. But the operation of NMR, sample insertion to running the program to obtain the data, it is as easy as operating a UV visible spectrophotometer. Absolutely fine, because both work on the same principle. Most of the operations are taken care by software only. Regulatory compliance. NMRs right now, whatever are available, starting from software to operation, all can be validated. Regulatory compliance is a possibility. Dependable output, time and sample. So output is always dependable. And then time, as I told you, you require just 10 minutes or below 10 minutes to capture the spectrum and also to give you the output. How much sample is needed? Less than 5 milligram. Approximately 5 milligram of the sample is sufficient for us. Less carbon footprint. How much solvent is needed? We require 1 ml of the deuterated solvent usually. Okay, so for preparation of the standard sample, because standard sample we use repeatedly. Okay, so normally in case of NMR, we take 0.5 ml of the sample or mixture in the NMR tube. In the 0.5 ml means 500 microliter. Whenever you are adding internal standard, the usual protocol is 100 microliter of standard mixture and 400 microliter of test sample is taken in the NMR tube. So total 0.5 ml only. Okay. So hardly 1 or 2 ml of the solvent is consumed. Cost per sample. Once the method is developed, for method development, we may have to run. Just now you have seen how many samples we are running, how many times we are running. That may be around, that may appear like costly, but once the method is developed, for running the samples, including cost of running, if you take into consideration, it will not go beyond 1,000 rupees. So friends, this is the way how qNMR is now emerging as a technique, a popular technique in analysis of especially complex mixtures. For example, you have a plant extract like Rauwolfia serpentina extract is there. I wanted to know how much quantity of reserpine is there and its congeners are there. Then qNMR can straight away give you the answer. Okay. Let us say if you wanted to go for HPLC, we usually don't prefer extract to be run on analytical HPLC column because an extract contains more than 100 compounds. Some of them are highly non-polar, some of them are highly polar. So your column is going to be damaged if you run crude organic plant mixtures. But in case of NMR, you simply have to dissolve the sample in appropriate deuterated solvent and run the proton NMR. Okay. Now we are working on one more technique which can be used as a quantitative technique. That is what we call it as DOSV, DOSI. It can help you even furthermore. That also can be completed within half an hour to 1 hour. So with this, I'll conclude my presentation. So I hope I made myself clear before you to propose qNMR as one of the, in future, because as a director of NMR Research Center, for the last 5 years, if I closely observe the market, the number of samples coming to our center for qNMR analysis are consistently increasing for different reasons. Let us say a production unit is there where they wanted to know what is the proportion of starting material and ending material. How much quantity of solvent is there in the product to be exported? So all these are the problems which earlier they used to do with many other techniques. Some of them, like solvent impurity, if it is there, it cannot be done by using a single analytical technique. Solvent can be evaluated with GC, and then sample can be evaluated by using HPLC. Multiple techniques are to be used. So there are so many complicated issues are coming where qNMR is offering a lot of hope. So friends, I hope I made myself clear, and this is what is qNMR. So if you have any doubts or queries, please raise. The session is now open for discussion. Thank you.
Thank you, sir. Thank you for your valuable insights in quantitative NMR. It is a very wonderful presentation. So participants, do you have any question? You can ask. You can unmute yourself and you can ask. Any questions from the participants?
Okay.
Sir Bhaskar.
Sir, thank you. Thank you, Dr. Murali Krishna Kumar garu. Your informative and very important presentation, sir. In spite of your busy schedule, you have accepted our invitation for the benefit of our faculty fraternity, sir. So it is a very important presentation for the pharmaceutical analysis faculty is concerned and chemistry is concerned, sir. Thank you so much, sir, on behalf of our management, faculty and students.
Thank you.
Thank you, sir.
Sir, can I sign out?
Yes, sir. Yes. We'll close the presentation. Thank you, sir. Thank you all.